Something interesting happens whenever you have a sample of pure water. Water molecules are obviously always moving, so what can happen is whenever one water molecule bumps into another water molecule, if they collide with sufficient energy and the right orientation, what can happen is one of these waters can actually lose a hydrogen to another water, forming that hydronium ion and some hydroxide ions. Now this is happening in all samples of water, so pure water is going to contain at least some hydronium and some hydroxide ions dissolved in it. Since this happens on its own, we've actually created, well, I guess not created, but more derived its own equilibrium expression for this process. This process is called the autoionization of water. One of the few things in life that just makes sense. Water is automatically ionizing itself. So we call this not just K, we call it Kw when we go to write the equilibrium expression for the autoionization of water. So like any K, it's going to equal the concentration of the products, which in this case are H3O plus and hydroxide, OH minus. However, there's not going to be a denominator because both of the reactants are liquids, and liquids are not written in equilibrium expressions. Now, interestingly enough, at 25 degrees Celsius, we've actually found that this value for Kw equals 1.0 times 10 to the negative 14th. That's a tiny K, so think about what that means in terms of this equilibrium. K is tiny, 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 so it's very much reactant favored. There's hardly any of this hydronium or hydroxide. That doesn't mean there's none, there's just so little of it. Well, why that's helpful is if we know the value for Kw, which we do, we should be able to find the values for H3O plus and the OH minus ions in pure water. So let's start plugging things in. Let's plug 1.0 times 10 to the negative 14th in for Kw. So 1.0 times 10 to the negative 14th, and that equals, now I want you to think about the concentrations of this hydronium compared to this hydroxide. For every one hydronium that was formed, one hydroxide had to be formed because it's a 1-to-1 ratio. So really that's just Mr. Engel's long-winded way of saying whatever the hydronium concentration is, it must also, that's a terrible equal sign, must also be equal to the hydroxide concentration. For that reason, we can just call them X. We can call the hydronium X and the hydroxide X, and as any good mathematician would do, X times X is X squared. Now, we can take the square root of X squared and the square root of our Kw, and that's going to solve for X, which in this case is equal to the hydronium concentration and also the hydroxide ion concentration. So X equals 1.0 times 10 to the negative 7th, and since that is a measurement of concentration, we need to put a unit on it, and that unit is molar. Now you've just discovered something huge. You've discovered in pure water the concentration of H3O plus. We already knew it was the same as the hydroxide, but now we've discovered that they're both 1.0 times 10 to the negative 7th molar. So something else to consider here. If this magical Kw, which is equal to H3O plus times hydroxide, since this value is a constant, that, that 1.0 times 10 to the negative 14th, since it's a constant, that means that if the H3O plus changes, the OH will have to change in order to maintain this constant value. So what that means is as the hydronium, let's say it were to increase, as hydronium increases, then the OH, the hydroxide concentration, must decrease to offset that change, and vice versa. If one of these two values here goes up, the other has to go down, and if one goes down, the other has to go up. And that actually allows us to do a little bit of calculations here. Let's say, what is the hydronium ion concentration if the OH concentration is, let's just say, 1.0 times 10 to the negative 12 molar. Well, again, we know Kw has to equal the hydronium concentration times the hydroxide concentration. We know Kw is 1.0 times 10 to the negative 14th. We're looking for the hydronium concentration, but we know the hydroxide concentration to be 1.0 times 10 to the negative 12. So since we're just trying to solve for this hydronium concentration, let's get it by itself. We'll divide both sides by 1.0 times 10 to the negative 12. 1.0 times 10 to the negative 12. And we'll find that this hydronium concentration is actually equal to 1.0 times 10 to the negative second. So we're able to find a hydronium concentration only from knowing a hydroxide concentration. And one more thing to consider, if we go back for a moment, ordinarily in pure water, both of these concentrations are equal to 1 times 10 to the negative 7th. So in this case, our hydroxide is now 1.0 times 10 to the negative 12th. That's a significant decrease in the value of our OH concentration. To offset that, we should see a significant increase in our H3O plus concentration, which we do, because 1.0 times 10 to the negative second is significantly larger than 1.0 times 10 to the negative 7th. And one last thing to consider here, when your hydronium concentration is equal to your hydroxide concentration, then you're dealing with a neutral substance, which makes sense. We've kind of touched on the fact that this is the acidic component and this is the basic component, so it makes good sense if your acidic component is equal to your basic component that you're going to be neutral. Well, we know as one of these goes up, the other has to go down. So what that means is any time that this H3O plus concentration is above or greater, let's use greater than, I like greater than better. Oops, that's not the eraser. Is greater than 1.0 times 10 to the negative 7th, that means you're going to have an OH concentration that is less than that value. Again, I'm not really sure why. Here, let me just start over on that part. Much better. If you have an H3O plus concentration greater than 1 times 10 to the negative 7th, that means you have to have an OH concentration less than 1.0 times 10 to the negative times 10 to the negative 7th. So that means your H3O plus must be greater than your OH minus in a scenario like this. And when that happens, you're acidic. You're dealing with a solution that's acidic because you have more acidic component than you do basic component. The opposite is exactly true as well. If your H3O plus is less than 1.0 times 10 to the negative 7th, then your OH must be greater than 1.0 times 10 to the negative 7th, which if you think about what that means your OH concentration will be greater than your H3O plus concentration. And again, you have more basic component than you do acidic component, so it makes good sense that you're dealing then with a basic solution.